Welcome to your sixth lesson. I'm Professor Seth Frey, and today we're going to learn about conditionality. So, to date, we've learned all kinds of things we can do with code flow. We've learned to build complexity from the very basic elements you start with and slowly do more complex things. We've learned how to take a list of things and go through it and do the same thing to each of them. We've learned to simulate code flow in our heads. And now we're going to add another twist to code flow, which is the ability to only run some of your lines of code if certain things are true. Otherwise, do nothing or do something else. This is a lot of the basis of the logic behind code. If then else, and you'll get more and more comfortable with that. We're going to take it real slow. And we're going to learn it very much in the context of an application. Just like it's common to have a list and want to do the same thing to every element in the list, it's very common to have a bunch of things, have a list, and only want a couple things from that list. Out of all the people in the room, I only want to congratulate the ones who have graduated. Of all the people trying to get into a bar, I only want to let in the ones who are of age. So this filtering is going to be our sort of initial use case, our main use case for introducing the idea of conditionality in Python. So what does filtering look like? So we're familiar with this syntax here. X for all x in y. Now we're just going to add a little bit. X for all x and y if z, if something's true. So if something about x holds, then we'll include x or we'll do that thing to x. If not, we're going to skip it. That's what this is going to look like. So we remember our days of the week example. We took the abbreviation. So for every day in days, take the first three letters. Now what we're going to do is, given this days list, which appears right here, we're going to just return the day, the unchanged. We're going to return the day for every day in days if day sub 0, that's going to be the first element of the string, equals capital S. So what's this going to do? It's going to return the entire the entire word, the entire string, if it begins with an S. We're going to get back the S days. Let's run it. There we are, Sunday and Saturday. Let's say I just want the abbreviations of the S days. We learned how to do that the first time around. And there you are, just the abbreviations of the S days. All that filtering down is because of this if. If I delete this if, we'll get all 7 days of the week back. So we can also, and that's what this example is here. Same thing. We combine the filtering and the editing to do more and more complex things. We've got another example, a word finder. So I have this word list, bandana, hyperboreal, blurb, defied, and so on. And what I want to know is, let's see, I want every W. So I just want the whole word back for every W in the word list if the very first element is equal to the very last element. Okay, so let's see. Bandana, no. Hyperboreal, no. Blurb, yes. Defied, yes. And so on. Polyp is going to come through, hopefully, and kayak. Let's run it. There, blurb, deified, polyp, and kayak. So again, we had a big list. We had a certain criterion that we were looking for. I wanted to know all the words that begin and end with the same letter, and that's what I got back, just in one line. We can do the opposite. We can get everything. This is the exact same thing, except that exclamation point means not. I want all the words that don't have the same first and last letters. So I'm going to get everything else in the list that wasn't in the first list. And I'll know and if I combine those two lists back together, I should get my original list back. That's what's going on here. I'm going to add words caught to words missed into a new word list. Now if I sort it and I sort my original, they should be identical if I sort them alphabetically. And there I get true back, which is to say these two lists are identical. I pulled them apart, I put them back together. Everything makes sense. Now I've got a third example, a little more word finder. I want to give another example of the kind of conditionality you can put after that if statement. Let's say I just want the SAT words. I just want, basically, I want to return a word if it's long, if it's got a lot of letters, it's a big fancy word. So let's just get the SAT words back. There they are, the two longest words, the two words more than 10 characters, are hyperboreal and cantankerousness, not cantankerousness. So this is our introduction to conditionality. We are building very, incrementally off of something we're already comfortable with, and pushing it further to show more and more things we can do with it without adding that much more complexity. So moving along, having learned our first introduction to if in this very concise one-liner format, it turns out we can extend that just the way we extended the for loop, using this indenting to build the longer, sometimes more readable form. And it just follows the same format we learned before. You say if something, colon, and then you do some spaces, do something. It's just the same thing, this whole indented format. But before, everything, when we did the for loop, everything in the indent got run on every element sort of in the list. Now, that everything in the indents, something really different happens to it. It gets run if the if is true. It doesn't get run otherwise. So the fact of the block makes everything subordinate to whatever's going on in this first line. And if it's a for loop, maybe it'll get run lots of times. If it's an if statement, maybe it won't get run at all. To give you some examples of that, the true and false themselves have true or false values. So the value of false is false. If false, print pancakes. This is a great way to make a line that does nothing. Nothing happened. If I change it to true, I'll get pancakes. Now, there's more than just true or false evaluate to true and false. Other things can evaluate to true and false. For example, this right here, this condition, age is greater than or equal to 21. Well, is it? Right now it gets replaced, it's defined as 30. 30 is greater than 21. So this, Python's going to read this and it's going to think, oh, well, that's the same as true. If true, so I am going to open the door. Good, open door. Of course, if it had been 20, that wouldn't run. All right, great. Same here. If time is equal to 9, go to sleep. But if time is later than 9 or before 9 or anything besides 9, we will not go to sleep. Similarly, payday is on the 30th. We're going to have fun on payday. What's today? Well, it's 30. So this should run. Any other day, we're not going to have any fun because it's not payday. We don't have any money. You can also chain these together. So we've got 3 if statements, sort of one after another, and we're just going to run through all of them. So there's 3 lines that could get printed out. Are we going to get 3 lines printed out? Well, that depends on these if statements. Is 0 greater than 2? No, it's not. Python's going to see 0 greater than 2. It's going to think, oh, that's a false statement. It's going to type false, and it's not going to run things if they're false. Then banana. Is banana in Bananarama? Is banana a substring of Bananarama? Yes, it is. So I expect this middle line to get printed. Now what about 3 times 4 equal to 36 over 3? Well, 3 times 4, Python's going to see that and replace it with 12. And 36 over 3, Python's going to see that and replace it with 12. So 12 is equal to 12. And this is going to run. So math continues to work, and parentheses, you're allowed to put parentheses in an if statement, just like you're using them in any other expression. So what I should expect is I'm going to get 2 lines of output, the second 2 lines of output. I miss the 80s, math works. Wonderful. So building off of this, it's often the case, if something's true, I want to do something. Otherwise, just forget it. There's other times, if something's true, I want to do something. Otherwise, I want to do something else. So I reach a fork in the road. I'm either going to turn left or right. If it's nice out, if it's the road less traveled, I'll turn left. Otherwise, I'm going to turn right. So we have this syntax here, this if, and it's followed by else. Now what's going on is, if one of these 2 blocks is going to get run, either open door or turn the poor child back. Only one's going to get run. So if age is greater than or equal to 21, we're going to open door. If age is anything else we're going to get turned back. There it is, open door. Now if it's less than 21, we're going to get turned back. So these are connected. The else is linked to the if. And the fate of that second block is intricately tied to what happens in the if, that what happens to the first block. Other examples of what happens with else. If time is 9, we'll go to sleep. If time is anything else, we're going to stay awake. If age is 22, then that's true, and we're going to open the door. If payday is 30, we're going to have fun. If payday is anything else, we're not. Let's see. Now it's 29. It's the day before. We're not going to have any fun. We're very eager. Penny saved is a penny earned. Let's see. We've got 2 siblings. If sister's older than brother, sister's older. Otherwise, brother's the same age or older. Now, why do I say that? Same age or older. You might have just said sister's older, brother's older, but there is this edge case, this special case. What if they're the same age? Which block of code should run if these are the same age? Well, is 12 greater than 12? No. So that second block of code is going to run. It doesn't just run in the condition that brother's older. It also runs in the condition that they're the same age. So it's the second line that's going to run when they're equal, because it is false that 12 is greater than 12. Just like with the for loop, where the extended form allowed us to kind of do more complicated stuff than this really concise, elegant form, it's the same with the if statement. When we use the extended sort of indent-based form of the if statement, rather than tying it into this really concise for loop, what we get is the ability to do more stuff in every if block. So if one thing, I do lots of things. Otherwise, do lots of different things. So that's what we'll see here. Here's my state. Here's what's going on right now. It's 11 in the morning. I've had 0 cups of coffee. I've hit the snooze button 0 times. Now, what's going to happen next? Well, that depends on the values of these variables, on the content of the if statement. So let's see. If hour is less than 7, or hour is greater than 23. So if hour is time of day, well, it's saying that if I haven't woken up yet, if it's after 11 p.m. but it's before 7, I haven't woken up, if that's true, if hour is equal to something outside of waking bounds, I'm going to say go away. Then I'm going to say I'm sleeping. Then I'm going to hit the snooze button once. However, if it's equal to 7, equal to 23, or anything in between there, if it's during waking hours, then I'm going to print want some coffee? Then I'm going to say, I need coffee. Then I'm going to increment the numbers of cups of coffee. So let's see, with our 11 is between 7 and 23, so I'm going to be in the waking hours and want some coffee. And if I change it to 6, outside of waking hours, then I'm going to say, go away, I'm sleeping. That's one example of this extended form. We've got another. So let's see. Henrietta here is 26. Now, if she's older, it says if she's older than 25, she can rent a car. Separate from that, if she's older than 18, she can vote. Separate from all that, if she's greater than 25, she can rent a car. Otherwise, she can't. And we can't tell if she can vote. Just because she's not greater than 25 doesn't tell us anything about if she's 18 or not. So when I run this code, a couple of things should happen. If she's 26, all of these this block should run. This block should run, because 26 is greater than 25, 26 is greater than 18, and this block should run, because 26 is greater than 25. So we've run it, and we get all 3 lines. Now we take it down a notch to 25. What should happen? Well, 25 is greater than or equal to 25. It's still greater than 18. It's still greater than or equal to 25. So we should get the same output. I'm going to run this. We'll get the same output. All right. Now let's take it down another notch, 24. So now we're between 25 and 18. 24 is less than 25, but greater than 18. So this should not run. Henrietta cannot rent a car at 24. She can still vote. And because this no longer satisfies, we're going to get that second line. So we'll get 2 lines of output, this one and this longer one that we haven't printed out yet. And again, if we take her all the way down to even younger than 18, then we're only going to get one line of output, because this is going to be false right here. 17 is not greater than 25. It's not greater than 18. And because it's not greater than 25 here, we're going to run the else. And Henrietta can't rent a car. We can't tell if she can vote, but we happen to know she can. There we are. To give you a sense of how these interact, let's look really closely. Let's look at what's the difference between an if and an else and two ifs. I mean, that's something we're kind of teasing with. What's it mean to have two ifs chained on each other versus an if and an else? Well, if you have the if and else, only one of those blocks of code is going to run. If you have the two ifs, maybe they'll both run, maybe neither will run, maybe one will run. These are subtle differences that relate directly to getting work done in code. Being able to, and you'll know when you're looking at a problem, what makes sense? Should it be one or the other, or should I really allow both if both make sense? It's going to depend on what you're writing up. To give a sense of precisely how they're interrelated, I'm giving an example here of writing two if statements as if they're an if-else, what that really looks like. So we have here two siblings, Bo and Bala. Either Bo is older than Bala or not. What do we have? We have them equal in age, so we should get the second line of code. Now, this block right here does exactly the same. There's no value of Bo, of Bala, that could make this block and this block give different outputs. They're always going to give the same output. So here, this line and this line, the first two lines of those blocks are identical. The second two lines of those blocks are identical. The last lines of those blocks are identical. The only difference is the third line. The third line here is the else, which is tied to the if. If Bo's older than Bala, do one thing. If there's anything else happens, do the second block. The else says all that in just four letters. However, this second one does the same thing. What this does is this second if statement is the exact opposite of this one. This says Bo's greater than Bala. This says Bo's less than or equal to Bala. So it literally covers every case that the first doesn't. They're mutually exclusive. If one happens, we know that the other didn't. That's precisely what happens with if and else. And that's why this block here will always give the same output as this block here, no matter how old Bo is, no matter how old Bala is. Now our elements are simple enough. It's easy to learn what this is, but as we chain them together, they can get more complicated. We already learned about thinking through the logic of code flow, and we're about to do more of that. We're about to get plenty more of it. We're going to encounter communicating more complex ideas like what I do doesn't just depend on this or that, it depends on all three of these things being true. Or, that's one setup. Or there's this other setup where there's three things that could be true, and I'll go left instead of right if any one of those three holds. To get concrete, let's take a look. For our example here, we've got whether I get a job. Well, whether I get a job depends on two things. Am I a citizen? Or do I have a visa? If I'm a citizen, I don't need a visa to get a job. If I have a visa, I don't have to be a citizen to get a job. So only one of those two things has to be true. And that's why it makes sense to have this, have two if statements here, to structure it that way. If I am a citizen, I can get a job. If I have visa, I can get a job. It doesn't matter if I'm both a citizen and have a visa, impossibly. As long as one of those is true, will get job, which got initialized to false, will get changed to true. And then when I run this last line, it will be true that I will get a job, because at least one of those was true. If they're both false, I won't get a job, but if at least one is true, I will. That's one logical flow. Now I'm going to pitch you on the second logical flow, on the second way of organizing the code, where I'm going to show you what it looks like to nest, put if statements in each other, the same way we put things inside of a for loop. So here's the same setup as before. Will I get a job, true or false? I'm going to start off false. Am I a citizen? Do I have a visa? We're going to make it so that if I get a job depends on some relationship of am I a citizen or do I have a visa. Except this time we're going to make it so I have to have both. We're going to describe a world where to get a job, I have to be a citizen and I have to have a visa. That's what this looks like. If is citizen is true, then I'm going to run this code. And I'm going to see if I have a visa. And if that's true, then I'm going to run this code. We'll get a job as true. However, if I'm not a citizen, then this code here is never going to run. And conversely, if I don't have a visa, then even if this code, even if this is true and this code runs, this if statement won't be satisfied, so this will not run. Both of those have to be true. Now, is that an accurate description of what it seems to get a job? No. No, it's not true that both conditions have to be satisfied for me to get a job. It's only true that one of them has to be satisfied. So this is a good model of the world. This setup of the logical flow is an accurate description of reality. This setup of the logical flow for this example is not an accurate description of reality. However, we can just flip that right around and show the opposite example where it does make sense to have the other logical flow. So what we've got here, we'll do the first flow first. If it looks like a duck, walks like a duck, quacks like a duck, is it a duck? According to this logical flow, if it looks like a duck, it doesn't matter if it walks or quacks like a duck, it's going to be a duck. If it walks like a duck, it doesn't matter if it looks or quacks like a duck. So of these three conditions, only one has to hold. It has to either look, walk, or quack like a duck to be a duck. Now that's one description of reality. That's one model of this scenario. That you don't need all three to hold, you only need one to hold. Let's look at the opposite. In this scenario, if you look like a duck, if you don't look like a duck, then no matter what happens after that, if you don't look like a duck, no matter what happens after that, this indented code's never going to run. Even if you do look like a duck, that's still not enough to guarantee it'll run. We still have to pass this other test that it walks like a duck. And again, if it walks like a duck, maybe it is a duck. We still have one more test. But if it's not a duck, even if it looks like a duck, even if it quacks like a duck, this inner code is never going to get written, and we can guarantee that it'll never get that is a duck will never be set to true. Only if looks like a duck is true, walks like a duck is true, and quacks like a duck is true, will I sort of descend all three, 1, 2, 3 levels of indenting to set is a duck to true. So this is our alternative model of reality, that all three have to hold, and this is how we represent that idea, that there's several criteria that have to hold for something to happen. This represents the idea that only one of many criteria have to hold for it to happen. This criterion made sense for getting a job. You either have to have a visa or you have to be a citizen. This one here makes sense for being a duck. You have to look and walk and quack like a duck to be a duck. So these different flows map on to different aspects of reality, and this is how we start communicating real ideas about the world and reality in code. And here we have those exact same two examples. What I've done is I've inserted print statements in each, so you can really see what's happening. If you get into looks like a duck, it's going to say so. If you got into walks like a duck, it's going to say so. It's going to say so here. So if these are all false, then none of those should run. If these are all false, we shouldn't get any output. None of those will run. Let's see. How do we get quacks like a duck to print out quacks like a duck? What has to happen? Is it enough to set quacks like a duck to true? I'm going to run it, and still nothing happened. I got no output. That's because for quacks like a duck to be true, it's not just enough that this is true. I have to have gotten to this block in the first place, which means I would have had to pass this test and this test. It's pretty easy to get looks like a duck to say true. I just have to set that to true. And to get walks like a duck to be true, looks like a duck has to be true as well. Only by setting both of these to be true can I get walks like a duck to print out as well. Looks like a duck, walks like a duck. So print statements are really good. You can just sort of, if you're not, code flow gets more complicated, right? Some code's being run, some's not being run, some's being run lots of times. That can be hard to keep track of, especially it's not so visual. It's hard to see it. Using these little print statements by just typing things in that give you a little peep when a certain block of code gets run is a very, very common debugging strategy. It's a very safe, sane approach to understanding what's going on in your code. It's all too common to write a bunch of code and then realize afterwards you have no idea what it does. By using these little diagnostic tricks, putting print, we can again get further insight, essentially start to visualize and get a better imagination for code flow, which is absolutely essential as we get into more complex subjects like conditionality and filtering down complex lists. Now I'm going to give you a chance to try it. So you've seen if in its short form where we used it in list comprehensions to filter. You also saw it in its longer form where we did sort of toy examples to show the logical flow. Now we're going to do the long form of list filtering. We're going to use our long for loop, right? Our indented for loop where for every element of a list we run the block of code. And inside that block of code is going to be an if that has its own block of code. For every element of this list, we're either going to go left or right or go up or down depending on the specific value of that item, and we can use that to sort out all the items in the list we don't want to keep and just keep the ones we do and put those into a new list. What I'm going to do, I'm going to take the examples I gave you in the very first section and we're just going to reproduce those examples in long form. So here we have our original code for the days. I wanted the days of the weekend, the days that begin with capital S, and I got Sunday and Saturday. Let's just do that exact same thing in long form. We're going to do it this way. First, we have our days list. That's the same. Now what I'm going to do, I'm creating a new list that's empty. Okay, it's our weekend abbreviations. So every item we want, we're going to put in that list using append, and the ones we don't, we won't put in. So for D and days, for every item in this list is if the very first element is equal to capital S, we're going to add it. We're going to add its abbreviated form. And we'll do that 1, 2, 3, 4, up to 7 times. All that's going to pass this test is Sunday, the very first element, and Saturday, the very last. So what we get when we run this last line should be a single list, sun, sat. Just the exact same output as here. We did it a slightly different way, but it's the exact same thing happening. We did it in longer form. So here's our second example. Words that begin and end with the same letter. When I run these, this is the same code we saw before. Blurb, defied, polyp, and kayak. Here's the long form of that. We've got words caught, which is going to be our sort of empty list. It's called initializing. We're initializing an empty list so that we can use it later and put things into it. If you're sorting through a pile of stuff, you're going to start with an empty bag to put the things you want to keep in. So we're initializing the empty bag so we can put things in it. For every word, for every W in word list, if the 0th element, the element at address 0 is equal to the element at -1, if the first and last elements are the same, then we're going to append to words caught, just like we want. And we'll get the same thing, blurb, defied, polyp, and kayak. How about bird words? Let's see. I want to know here, let's think through the logic of this. I've got a bunch of birds, the bluebird equal falcon, flamingo, and so on. Now for every bird in the bird words, if bird 0 is in A-E-I-O-U, let's see, what's that mean? A-E-I-O-U, that's not a word, so I'm not really looking for a substring in the familiar sense. What I'm doing, if bird 0, well, let's see. Bird 0 of bluebird is B. Is B in A-E-I-O-U? No. Is eagle E in A-E-I-O-U? Yes, it is. Falcon, no. F-F-K-R. What I think is going on here, as we put it together, we understand, we skim the code, is that what we want is we want all the bird names that begin with vowels. And we got eagle. And we could negate that. I only want bird names. I want to filter through all the bird names and only get the ones that don't begin with vowels. And I get everything except eagle back. So the really, ultimately the biggest difference between using the long form and the short form of filtering is that one's long, one's short. And that can be good or bad. It sort of depends what you're doing. Whichever is easier to read, whichever is easier to think about, maybe whichever is shorter or easier to write, or easier to return to 6 months down the line and kind of remember what it did. But by teaching you both, I help you triangulate the knowledge and the intuition. By showing you several syntaxes, several approaches to the same thing, you get closer and closer to getting a full picture of it and making it make sense for yourself. So hopefully that's enough to work with. Try this out and we'll move along. So having learned about filtering, nesting if inside of for, there's another useful thing that we can add to our toolkit, just with these basic elements. As long as we combine them in different ways, we can do more and more things. A really useful thing to be able to do is to compare two lists. I've got a bunch of first names, a bunch of surnames. How would I know if there are some names that are both first and last names? I would want to take both lists and kind of run through them at the same time. Or let's say I want to learn all possible names. I would want to take, for every element of the first list, I would want to run it by every element of the second list and assemble all combinations of first and last names. We're going to do all these things. So with just tiny changes in the next couple of code blocks, we'll do very different things. First, we're going to find out which first names are also last names. But let's solve this ourselves. Let's see. We can kind of skim it. I see that Akshay is a first and last name. I'm seeing Michelle pop out. And anything else? No. So ultimately, our final answer, we're kind of skipping to the end. We're using our intuition. We're using our own eyes, and we want to sanity check the code by making sure that what happens is what we expected to happen. So what we expect to happen is a list that says Michelle and Akshay and leaves out all the other names. How's this going to work? Well, we're going to start with our sort of initialize an empty list. Initialize the lists that meet this property of being both first and last names. Then for every n in the first name, if that name, whatever it is, it's going to start being Michelle. Then second loop, it'll be Elsa. We're going through first names. Third loop, it'll be Akshay. If n is in this list somewhere, then append it to the empty list and grow that list out. So let's see. Our first n is going to be Michelle. Is Michelle in surnames? Yes. So Michelle is going to get appended to universal names. How about Elsa? Is Elsa in surnames? Is Elsa in surnames? No, I don't see Elsa in surnames. So Elsa is not going to get appended. Akshay is. Marianne's not. Patricius is not. And Hamid is not going to get added. So when we run this code, we'll get our two names back. Michelle, Akshay. Let's see. Now we'll do the opposite. Which first names are not last names? I should get the opposite of what I got before. So I want the last only name. The names that are only appropriate as last names. Oh, sorry. This isn't the opposite. This is not the opposite of the last one. The opposite of the last one would have been which first names are not last names. It's different to say which last names are not first names. What we should get, suddenly we're looping through this list, and I want to know which things are not in the first. Well, let's see. Is Newt in the first? Is Reese in the first? No. Akshay is. Michelle is. Mateus is not. And Velimir is not. So, which last names are not first names? We initialize our last names only list. Then for every name in that list, if it's not in the first names, then we're going to extend our empty list and print that out. And we should get all the last names available except for Michelle and Akshay, which we do. Now there are other examples of going through two lists together. We can go through one to make sure it does or doesn't have elements in the other, that it doesn't correspond to items in the other. Or we can run every element of one list through every element of another. That's a different reason we would be comparing two lists. Why would we want to do that? Well, if you live in a generic, giant American suburban development, maybe you've noticed they have really generic names. There's Stone Gates and Oak Crests and Oak Creeks and Spring Fields and all these things. So what we're going to do, we'll come up with a suburban development name generator. We've got our modifiers, that's the first part of a suburban development name, and we have our geographic marker. Whenever you have these names, they always end in some kind of place like ridge or hurst or dale or crest. A hurst is a type of hill. So here's what we're going to do. For every modifier and modifier, so we'll go through green, then we'll go through oak, then we'll go through cherry. Then we're going to have another for loop inside of that for every feature in geography. creek, park, wood, brook, grove. Print the modifier plus the feature. And that's going to give us an exhaustive list of all suburban development names. Now, how's that work? For modifier and modifier. So modifier is going to be green. Okay? For the entire duration, I'm kind of going to write this out. Modifier equals green. Now, for the entire duration of this second for loop, modifier is going to be green. So we're going to get green creek, green park, green wood, green brook, green grove, green glen. And when we reach the end, green crest, that this inner for loop's done, are we going to go back up top to this and go to the second element? We were at green, now we go to oak. This is going to become oak. And now for the entire duration of this inner for loop, modifier is going to be oak. And we're going to do the entire thing again. Oak creek, oak park, oak wood, oak brook, and so on until we reach crest at the very end of this inner for loop, at which point we're going to go to the third element of the outer for loop, and modifier will become cherry, and on and on and on. So that inner loop, we went through geography once for every single element of modifier. We went through geography, the entire list of geography, lots of times. This is how we cross every single element of the first list with every single element of the second, by putting one for loop inside of the other for loop. And what we should get is a super comprehensive list of things that sound like suburban American cookie cutter McMansion type developments. I live in a let's see. I live in a stone gate. No, yeah, I didn't put gate in here, sorry. But maybe you'll find your development in here. Okay, so now we've seen all these kinds of things that if can do. We can use it to filter down a big list into a smaller one. We can do that in a long or short format. We can use if to chain together more complex ideas and express ideas like that several criteria have to be fulfilled, or that only one of several criteria have to be filled for me to move forward. Now that we have all these tools in our toolbox, we're ready to show something potentially useful. Maybe you like word games, Scrabble, or any of a number of mobile games. So you know that there's these letter tiles, and you have to arrange them in your head to form words out of them. Wouldn't it be great if we could automate that? I mean, your computer has a dictionary. What if I could just take those letters and look up all possible combinations in the dictionary? Cheat. I would learn a bunch more words. I would work really fast. I bet you a computer is much faster than the human at anagram type puzzles. So what we'll do here, having learned about if and how to build out of for with if, how to build better filters and that kind of thing, we're going to build an anagram detector. Now we're not going to get it right on our first try. I'm going to show you bad logic just like I showed you bad logic before. We're going to have things that kind of work and incrementally improve them until they really work. To do that, we're going to learn some basic bits. We've got our setup here. So first we're going to show that this metaphor that strings are lists, it's not just a metaphor. A string can be turned into a list of characters. What's the difference between a string, which is a list of characters, and a list of characters? Well, let's run this code right here. This is word, and this is word put into the function list. What we get word back in the first, but in the second we get the list of S, H, E, E, T, and S. So we can turn a word into a list, and that's a thing that's useful to do. We'll do that later. Here's another useful thing to do. We can take a list and we can take things out of it. We can remove green. Now, is remove green from colors, is that going to remove all greens, or just what's going to happen? It's just going to remove the first. So we still have the second green there. But with these two sort of list-related functions, one turns the string into a list, the other removes things from a list. We can build more complicated things, and these are going to contribute to our anagram detector. Now's a good time to move along to take one on our anagram detector. And here's our question: are itch and chit anagrams? A chit is a kind of it's like a chip, kind of. Itch and chit. Well, visually, they're both 4 letters long. They have an I, a T, a C, and an H. So they seem to me to be anagrams. And hopefully our code, if it's correct, is going to say, yes, Those are anagrams. All right, so here's word 1, itch. Here's word 2, chit. The way our code's going to work, I'm going to start off with this logical flow that we're going to assume all words are anagrams. All possible values of word 1 and 2 are anagrams until proven guilty, until proven otherwise. And then the purpose of the rest of this code is to prove otherwise, if it's not the case. So first thing I'm going to do, I convert word 1 to a list. I convert word 2 to its list. So now I have the list itch, the list chit, and where we're going to iterate through word list 1. Now, for every letter in word list 1, we're going to ask, is that letter not in word list 2? So if there's anything in word list 1 that's not in word list 2, it must be the case that those two words are not anagrams. And so we're going to set our anagrams to false. This will be our sort of test, our condition, to see if two words are or are not anagrams. What answer do we get? Well, intuitively, there are no letters in itch that are not in chit. So this should return true, and that's good because itch and chit are anagrams. Okay, that's great. Good news. Our code says true. So itch and chit are anagrams. I put them through my code. I got a true. And if I had added, an X here, X is not in chit, so I should get false. Okay, hey, that's encouraging. This is great news. Everything's wonderful. Look, we got it on our first try. Except, let's take a look at take 2. Or this second example of take 1. We've got itch and sheep. Those are really different, so I would hope those are not going to turn out as anagrams. So the exact same code is going to correctly say false, good. Itch and sheep are obviously not anagrams. Now, it's in this third example where we get a little tricky. Are itch and chiclet anagrams? Our desired answer is no, they're clearly not anagrams. However, every single letter in itch is in chiclet. There's the I right there, there's the T at the end, there's the C, and there's the H. So, starting with our anagrams true, our anagrams is never going to get set to false because for every single letter in word 1, that word is in word 2. This is never going to get set to false, and this code is going to register true. So our anagram detector is not perfect. Now, is it completely off base? Like a stopped watch is right twice a day? Is it just like lucky? Or is it kind of good down payment, good progress towards something that does work? I'm going to lean towards the second one because if two words are anagrams, this code is never going to say they're not anagrams. All that's wrong with it is sometimes it says words are anagrams when they're not. So we just have to fix that other half of the problem and we're good. This is what's going to bring us to take 2. So what makes two words an anagram? It's not just enough that all the letters in one are in the other, or even that all the letters in one are in the other and all the letters in the second one are in the first one. Because, I don't know, what's an example? Let's see, ab, like your ab muscle, AB, and ba, the sound a sheep makes, B-A-A. All the letters in the first are in the second, all the letters in the second are the first, but they're not anagrams because one's 3 letters long, the other's 2 letters long. There's different numbers of the letters, so they're not anagrams. And that's going to be our first thing. What we're going to do, we'll take our first failed anagram detector, and we're going to add 3 lines to it. I'm going to add this line here, a big if statement. I'm going to wrap my entire old code, that's all of this stuff, in an if statement. And that if statement is going to see if the words are the same length. Okay? If they're not the same length, no matter what, this else is going to run. If they're not the same length, no matter what, they must not be anagrams. If they are the same length, it could still turn out that they are or are not anagrams. We have to run more tests, and that's why we go back to our original code from take 1. So here's what's going to happen. Itch and chiclet. That failed test from before, we're going to run it again. And if we had just run this code, then we would still get true. But we're hiding that code. That code's never going to run if itch and chiclet are of different lengths. They are of different lengths. They must not be anagrams. This code is going to correctly return false. So is it perfect? Is there nothing that can break it? This is all going to bring us to take 3. where we're going to add one little twist. So read and read are clearly not anagrams, and the code above is going to say that they are anagrams because they're the same length and all the letters in one are in the other. Here we need to do more careful accounting. We really have to go one by one. Okay, is this letter in that one? If so, let's take it out of consideration. And now we'll look for another. Is it in there? If so, we'll take it out of consideration. And if for every single letter, we can remove that corresponding letter from the second word, and we do that for every single letter. If there's no letters left by the time we reach the end of the first word, we know that for a one-to-one correspondence, every single letter maps to every single letter. Those words are anagrams. If there's any letters left over, if there's any letters we didn't get, those words are not anagrams. So now we're going to walk through how this code works. Compared to take 2, take 3 just adds these 2 lines. To the previous if, our anagrams equals false. It adds an else. It's going to remove a letter once it's accounted for. So we have read, we have read. Are they anagrams? We'll set that to true and try to prove that they're false. By the end of this code, if they're not anagrams, this our anagrams variable should be set to false. So let's see, are read and read the same length? Yes, they are. So we're going to go into this block of code. If they weren't, we would already know right away they're not anagrams. All right, so they're the same length. That means that for every letter in read, I want to ask if that letter is in read. I'm going to start with R. R is in read with 2 Ds. So this is false. This asks if the letter is not in the word, and R is in the word. So what we're going to do instead is from word list 2, we're going to remove one R. And what we should get, read, is going to become ed. And we're going to reach the end of this loop, go back up here, and we're going to start on the second letter of the word read, which is E. Is E in ed, E-D-D? Yes, E is in ed, E-D-D. So I'm going to remove E, and I'm going to end up with D-D. Now let's see, for every letter in word list 1, now I'm on the second E of read. I've been through this loop 3 times, the second E. Are there any E's in DD, in the list DD? No, there are not any E's in DD. So our anagrams will be false, and we will have correctly determined, even though they're very similar to each other, and they passed every previous test, merely by adding these 2 letters, these 2 lines, we're able to show that those 2 words are not anagrams. So now we have like an actual definition of an anagram. Any 2 words, if they're the same length, if all the letters in the first are in the second, and if we can make it through the entire word removing one at a time and there's nothing left in the second pile, if we meet those 3 criteria, then a word is and always will be an anagram. So what we've built here with these lines, we built it incrementally. We've made a first tab, we found some mistakes, then we changed it and fixed some mistakes, but found some new mistakes. We slowly, incrementally built something until we built a pretty good detector of anagrams. It can't go wrong. We did that using the elements that we learned about today, if and all the things that you can do with if, else, the way you extend it with if, and the way it complicates and influences the logic, and we're able to build more and more complex things. Now in the process, sort of on reflection, let's look back at this code we wrote. If you just sort of started off with this code, you'd be a little intimidated. I'm seeing an if in a for in an if. That's a lot of stuff. But because we built it incrementally, we're able to sort of build our knowledge incrementally. And having been through this whole experience, this code is maybe still intimidating. It might be the longest code you've seen so far in a lesson. However, it's less intimidating than it would have been if you'd seen it all at once. We built it up slowly, and you became comfortable slowly with each element. And before you knew it, there is something that kind of looks impressive in front of you. And with that, we're at our summary. We're at the end. We've learned how to filter a list down to pull useful elements out of a longer list. We've learned the long and short forms of that. We've learned how to use if and else, and we've learned how to compare lists element by element, all towards eventually doing something useful. Taking two words, treating them both as lists, and comparing them element by element to determine if they're anagrams. So now that you've learned this additional element of code flow, this additional complexity, you don't just know how to take a block of code and run it several times for every element in a collection. You also know that you can sometimes run it, sometimes not, depending on whatever, depending on your model of the world. You can turn left or turn right, do A or B, and do increasingly complex stuff in code. With that, you've made it through lesson 6, and congratulations.